So we're almost at the finish line of our analysis of quicksort. Let me remind you what we're proving. We're proving that for the randomized implementation of quicksort, where we always choose a pivot element to partition around uniformly at random, we're showing that for every array, every input of length n, the average running time of quicksort over the random choices of pivots is big O of n log n. So we've done a lot of work in the last couple videos. Let me just remind you about the story so far. In the first video, what we did is we identified the relevant random variable that we cared about, capital C, the number of comparisons that quicksort makes among pairs of elements in the input array. Then we applied a decomposition approach. We expressed capital C, the overall number of comparisons, as a sum of indicator or 0, 1 random variables, where each of those variables, xij, just counted the number of comparisons involving the ith smallest and jth smallest entries in the array, and that's going to be either 0 or 1. Then we applied linearity of expectation to realize all we really needed to understand was the comparison probabilities for different pairs of elements. In the second video, we nailed what that comparison probability is. Specifically, for the ith smallest and the jth smallest elements in the array, the probability that quicksort compares them when you always make random pivot choices is exactly 2 divided by the quantity j minus I plus 1. So putting that all together yields the following expression governing the average number of comparisons made by quicksort. And one thing I want you to appreciate is in the last couple of videos we've been sort of amazingly exact as algorithmic analysis goes. Specifically, we've done nothing sloppy whatsoever. We've done no estimates. The number of comparisons the quicksort makes on average is exactly this double sum. Now, shortly we'll do some inequalities to make our lives a little bit easier, but up to this point everything has been completely exact. And this lets you see why there's small constants also in quicksort. It's basically going to be this factor 2. Now the next question to ask is, what are we shooting for? Remember, the theorem we want to prove is that the expected number of comparisons, really the expected runtime, is O of n log n. So are we already done? Well, not quite. We're going to have to be a little bit clever. So if we look at this double sum, and we ask how big are the summands and how many terms are there, well, the biggest summands we're ever going to see are when I and j are right next to each other, where j is 1 bigger than I. In that case, this fraction is going to be 1/2. So the terms can be as big as 1/2. How many terms are there? Well, there's a quadratic number of terms. So it'd be very easy to derive an upper bound that's quadratic in n, but that's not what we want. We want one that's n log n. So to derive that, we're going to have to be a little bit more clever about how we evaluate this sum. So the idea is what we're going to do is we're going to think about a fixed value of I in this outermost sum, and then we're going to ask how big could the inner sum be? So let's fix some value of I, the value of the index in the outer sum. And then let's look at the inner sum, where j ranges from I plus 1 up to n, and the value of the summand is 1 over the quantity j minus I plus 1. So how big can this be? Well, let's first understand what the terms actually are. So j starts at I plus 1, and then it ascends to n. And as j gets bigger, the denominator gets bigger, so the summands get smaller. So the biggest summand is going to be the very first one when j is as small as possible, namely I plus 1. When j is I plus 1, the summand is 1/2. Then j gets incremented in the sum, and so we're going to pick up a 1/3 term, followed by a 1/4 term, and so on. So it's going to be, for every inner sum is going to have of this form, 1/2 plus 1/3 plus 1/4, and then it's going to sort of run out at some point when j equals n, and the biggest term we're ever going to see is going to be a 1 over n, in the case where I equals 1. So let's make our lives easier by taking this expression we started with, star, and instead of having a double sum, let's just upper bound this with a single sum. So what are the ingredients of the single sum? Well, there's this 2, can't forget the 2. Then there's n choices for I. Actually, there's n minus 1 choices for I, but let's just be sloppy and say n choices. So that gives us a factor n. And then how big can an inner sum be? Well, an inner sum is just a bunch of these terms, 1/2 plus 1/3, and so on. The biggest of those inner sums is the one occurring when I equals 1, at which point the last term is 1 over n. So we're going to just do a change of variable and express the inner sum, an upper bound on each inner sum, as the sum from k equal 2 to n of 1 over k. So that's looking more manageable, just having this single sum involving this index k. And life's going to get really good when we prove the next claim, which is that this sum cannot be very big. It's only logarithmic in n. Even though there's a linear number of summands, the overall value of the sum is only logarithmic. That, of course, is going to complete the proof because that'll give us an overall bound of 2 times n times the natural log of n. So that's an n log n bound with really quite reasonable constants. So why is this true? Why is this sum only logarithmically large? Well, let's do a proof by a picture. I'm going to write this sum in a geometric fashion. So on the x-axis, let me mark off points corresponding to the positive integers. And on the y-axis, let me mark off points corresponding to fractions of the form 1 over k. And what I'm going to do is going to draw a bunch of rectangles of decreasing area. Specifically, they all have width 1, and the heights are going to be like 1 over k. So the area of this guy is 1, the area of this guy is 1/2, the area of this guy is 1/3, and so on. And now I'm going to overlay on this picture the graph of the function, the continuous function f of x equals 1 over x. So notice that is going to go through these 3 points. It's going to kiss all of these rectangles on their upper right corners. Now what is it we're trying to prove? The claim we're trying to prove is that this sum of 1/2 plus 1/3 and so on is upper bounded by something. So this sum can be just thought of as the areas in these rectangles, the 1/2, the 1/3, and so on. And we're going to upper bound it by the area under the blue curve. So you notice the area under the blue curve is at least as big as the sum of the areas of the rectangles because the curve hits each of these rectangles in its northeast corner. So putting that into mathematics, the sum from k equal 2 to n of 1 over k is bounded above by the integral, and we'll start the area under the curve at 1, and then we need it to go all the way up to n of the function 1 over x dx. So that's the area under the curve. And if you remember a little bit of calculus, the integral of 1 over x is the natural log of x. So this equals the natural log of x evaluated at n and 1, also known as log n minus log 1. And of course, log 1 would be 0. So that gives us our log n. So that completes the proof of the claim that indeed the sum of these 1 over k's is bounded above by the natural log of n, and that in fact completes the proof of the theorem. We've got that the expected number of comparisons is at most 2n times this sum, which is at most log n. Putting it all together, we find that the expected number of comparisons that Quicksort makes on an arbitrary input of length n is 2 times n times the natural log of n. So that would be big O of n log n with quite reasonable constants. Now this is just the number of comparisons, but as we observed earlier, the running time of Quicksort on average is not much more than that. The running time is dominated by the number of comparisons that it makes. Moreover, as we discussed when we were talking about the details of the implementation, it works in place. Essentially no extra storage is necessary. So that is a complete and mathematically rigorous explanation of just why Quicksort is so quick.